Okay, so good morning. Today I'm going to show you guys about patterns. Oops, just dropped my thing. Alright, patterns. Chapter 9-1 in Algebra 2. So there's two different kinds of patterns. Well, there's two kinds of formulas for patterns, I should say. Two that we'll be looking at right now. One's called explicit and one called recursive. And explicit is the better kind. And I'm going to start with that one. And first problem goes like this. A pattern has an explicit formula of a of n equals 3n minus 2. What are the first 10 terms of the sequence? Okay, so they gave me the explicit formula. So if I have the explicit formula, you can find out everything, which means the first term, a of n represents, any term you want to find. So if I want to find the first term, which I'll call a of 1, that means I'm going to take 3 and I'll plug in 1 for n. Okay, so if I plug a 1 in there, I'll get my first term. 3 times 1 is 3. 3 minus 2 is 1. If I want my second term, I will plug in 2. 2 for n. 3 times 2 is 6. 6 minus 2 is 4. A of 3 is what I'll get when I plug in 3. 3 times 3 is 9. 9 minus 2 is 7. If I want to find the fourth term, I plug in 4. And 3 times 4 is 12. 12 minus 2 is 10. All right, so this is the sequence. Now you can sit there and keep doing those out. However, at a certain point, I'm looking at this pattern. I'm going 1, 4, 7, 10. Okay, so I'm adding 3 every single time, which means I know the next number after that is going to be 13, and then 16, and then 19, and then 22. And have I gotten to 10 yet? 1, 2, 3, 4, 5, 6, 7, 8. No, I need 2 more. 25 and 28. We'll finish it out. Or you can plug in all those numbers all the way to 10. All right, so that's the first one. And that's your introduction to an explicit formula. And the beautiful thing about an explicit formula is you can do problems like this one, number 2, where it says the sequence has an explicit formula of a of n equals 12n plus 3. What is the 12th number in the sequence which sometimes is called a of 12. Okay, so the nice thing about this, once you have the formulas, you don't have to do out, all of the numbers. I have the formula, and if I want to know what the 12th number is, I plug in 12. If I want to know what the 100th number is, I plug in 100 for n, okay? N represents, which number in the sequence it is. If you want to know the 200th number, plug in 200 for n. So once you got the explicit formula, you can find out everything, and that's why it's the best. Much better than recursive. So anyway, 12 times 12 is 144, and 144 plus 3 is 147. And that's the answer. I should change that from a of n to a of 12 to be correct. Okay, there we go. We good? If you have questions, check with me later. All right, so that was my second problem. Third one, this one has to do with recursive. What is a recursive definition for the sequence? And the sequence is 1, 3, 6, 10, 15, 21. Okay. So recursive is not as good because, if I asked you to find the 100th term, you wouldn't be able to do it without finding the 99th term. However, it's easier, especially for some of the harder sequences like this one, for example, where, if I'm looking at what's the pattern here, to go from 1 to 3, I add 2. To go from 3 to 6, I add 3. To go from 6 to 10, I add 4. 10 to 15 is 5. So there's definitely a pattern here. It's a pretty easy one, right? I'm adding, all the numbers up, add 2 plus 3 plus 4 plus 5. Which means, if I'm looking at, this is the recursive. If I take a of n, that's going to be the number in the sequence that I'm looking for. And we're adding up all the numbers. I'm adding 2, then 3, then 4, then 5. There's a thing that we represent in sequences for that, because I'm getting all of the numbers. It's called n, all right? So if I take n and I add the last number in the sequence, which would be a of n minus 1, and that's what we use in the recursive to represent the last number in the sequence. Okay. Now n, because this is the first number in the sequence, this is the second number, this is the third number. You can see where we keep adding that n over and over again to get the next number. All right, so that would be the recursive formula for that. Okay, so I want to know the fifth one. I'd add 5 to the fourth number in the sequence. The fourth number in the sequence was 10, so I'd add 5 to 10 and get my 15. And if I want to know the sixth number in the sequence, I'd be adding 6 to the fifth number, which is 15. So you can see how we get the next number. However, it's not as smooth as the explicit. All right. So back to the next one. Number 4. Find an explicit formula for. And I'll give you the pattern. It's 2, 4, 6, 8, 10. And dot, 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 which means it keeps going on and on and on. All right, so a of n equals what? And for some of these, I'm just going to let you play with them. There is more coming up about, arithmetic and geometric sequences. Arithmetic means you're adding over and over again. Geometric means you're multiplying over and over again to get the next number in the sequence. But, with some of these, you can just play with it and figure it out, If you find the gap here, I'm adding 2, adding 2, adding 2 over and over again. Okay, so since the rate of change is going up 2 every single time, this is a of n equals 2n. And if I plug in, the idea is if I plug in 1 for n, you should get the first number in the sequence. If I plug in 2 for n, I should get the second number in the sequence. 3 for n should give me the third number, and et cetera, et cetera. How about number 5 here? Same idea, same directions, except my sequences 6, 8, 10, 12, 14. So once again, this is going up by 2's. plus 2, plus 2, plus 2, plus 2. So, you can start by going, whoops, a of n equals 2n, right? Now, that takes care of the spacing. The problem is it doesn't start in the right place. Like I said, if I plug in 1 for n, I should get 6. But 1 times 2 is 2, which means, you got to, add some stuff or change it around. Since I got 2, and I actually want it to be 6, really I should add 4 to it. So if I go like this, what happens then? Does it work then? And I got 2n plus 4. Well, that does actually equal 6. And now if I change that to a 2, I get 8. And if I change it to a 3, I get 10. All right, so that takes care of the problem for that one. And there's the explicit formula, which of course is the best one. So I want to know what the 100th number is. Just plug in 100 for n, and you'll get your answer. Okay, let's do some number 6. Write an explicit formula for 1, 3, 5, 7, 9, ... Means that pattern keeps going on and on. All right, so it looks like odd numbers. Once again, spacing is 2, right? If I add 2, add 2, add 2, add 2, which means if I start that same way, a of n equals 2n. But if I plug in 1, I get 2. If I plug in 2, I get 4. Which means all these numbers are 1 less than those numbers. So if I go 2n minus 1, I'll get 2n1. 2 times 2 is 4. 4 minus 1 is 3. So that works. In fact, when you get up into higher math, this is the definition for an odd number, 2n minus 1. And, if I'm looking for the definition of an even number, it'll be 2n. All right, sometimes it'll be 2n plus 1 or 2n minus 1. Either way, you get all the odd numbers. Just something to keep in mind, especially for those of you going on in math. All right, so that's a little more than you need to know perhaps, but it's nice for this kind of problems. All right, next, number 7. Write a recursive definition So this is the most famous pattern in history, and this is called the Fibonacci sequence. And the reason why it's the most famous one in history is because it shows up in nature. It shows up in pine cones, and it also shows up in sunflowers. And so because, if you count the bumps on the pine cones, you find this Fibonacci sequence, and because of that, it's the most famous one in history. Now, how you get the Fibonacci sequence, sometimes it jumps right out at you, is if I take the first two numbers and I add them together, I get the second number, the third number. And if I take the second and the third number, I get the fourth number. So if I add these two together, I should get the 5. Okay, so you see how that works? You have to be able to recognize the pattern first. Add the two numbers before it, and you get the one after it. Which means, if I'm writing a recursive definition, so recursive definition has an a of n, and it usually has an a of n minus 1. So this would be the number before it. So I don't just take the previous number, I need to add the one before that to it also. So the one before the previous number would be n minus 2 would be, the second one before that, the one before that, and the one before that. So if I add those two together, then I get the next number. So this would be your recursive definition for that. Next one, number 8. Write a recursive definition. Let's do this as a U try. Okay, so you try. Hit pause, come back. Okay, welcome back. So sometimes if you want, you can always, make this into a table. I got n, here's a of n. First number in the sequence is 1, second number is 2, third number is 6, and I can keep going. 4 gives me 24, 5 gives me 120, 6 is 720. Sometimes that's easier, believe it or not. So when I take this recursive, if I take the number before it, what did I do to get it? Well, I took, I multiplied the number after it with it, the n formula here, if I was looking for the previous number, if I took this and I multiplied it by that, I would get this number, the 2. If I took this 2, which is a of n, now it's a of n minus 1, multiplied by 3, I get 6. If I took 6 times 4, I'd get the 24. 24 times 5 gives me 120. So what you're actually doing is taking a of n minus 1, the previous number, and multiplying it by n. So that would be your recursive definition. Change the color on that. Put a time sign in there. So that's the recursive, that's it. Do I dare do this one? All right, we're going to go for it. What is a recursive definition for I did this with an explicit actually. It's about as hard as they get at this level. So, the first thing that is going on is I'm multiplying by 2, right? There's a couple things going on. I'm multiplying by 2, and then I'm multiplying by 4, 9 times 4, and then I'm multiplying by, 9 times 8, which is really the powers of 2. So if I took the powers of 2 and I multiplied it times 9, I get the multiples of 9. So that's part of this formula. Now, the first thing is if I plug in 1, remember the first number, when you plug in 1, you should get the first number. Now, if I plug in 1 for n right now, 9 times 2 is actually 18. So I got the second number in the sequence instead of the first number. And if I plugged in 2, I get 4 times 9 is 36. So there's the third number. So I'm off by a number. And there's a nice trick for that. Is if I subtract 1 there in that exponent, you know, I get, now if I plug in 1, I get n, this will be 0, which anything to the 0 power is 1, which means I'll get 9 when I plug in the first one. So now it'll move me back 1 in the sequence. Now the other thing that's going on with this pattern is, you know, that this goes positive, negative, okay? Which means, you know, if I take -1 and I take it either to the n or to the n plus 1 power, that'll take care of the positive negatives. Suppose I put n, that will make the first one will be negative. So I'm actually going to go n plus 1. And if I plug in 1 now, I get -1 squared is positive 1. -1 to the third power will give me the second one, which will be negative. And that's what I get. Now, there's different ways to write this. You know, you can pop that -1 in there, in with the 2. That's one way to do it, but I wrote it separately just so you could kind of see that. So if I connect it all by multiplication, that's actually one way to write that equation. So these start getting more complicated as you go up in math, and they can be a lot of fun to play with. I enjoy playing with them, some in graduate school and college math and stuff. So anyway, that's the way I'm going to end it today. Thank you very much for watching, and see you all soon.